Good day to our beloved lecturer, Dr. Chong, and to all my fellow friends. My name is Bryan, and together with me, SIAK Chun Shi, would like to talk about our material selection and sustainability assignment. So, to kickstart, I'd like to move on to the introduction. The product that we have selected is badminton racket, which is categorized under the sports and recreation equipment. And badminton racket is a fundamental instrument for the sports of badminton, which is a game with historical roots in ancient civilization but modernized in the 19th century in British India. The transformation in design of badminton rackets over time is noteworthy. From early rackets made of solid woods, the manufacturing process evolved through steels, aluminum, and now carbon fiber composites, providing us with lightweight and durable rackets. And now I'll move on to the product applications. So for the product applications, badminton rackets' primary function is to hit the shuttlecock at a distinctive projectile in a game of badminton. And the construction and materials would impact the weight, stiffness, and overall performance of the racket. And its use requires agility, accuracy, and strategic awareness. So here is a diagram of a badminton racket. And in this diagram, we can see that the biggest coverage is the badminton frame for the badminton racket. And now I'll move on to the key properties. So for the key properties required in badminton frames are the materials density, tensile strength, fatigue strength, stiffness, and as well the cost. The density of materials is defined as the materials mass per unit volume. The weight of the badminton racket should varies from 59.9 grams to 90 grams. And this is to ensure that we can produce a lightweight and easy to handle single-handedly badminton racket. And next is the tensile strength. Tensile strength is defined as the maximum stress that can be sustained by the structure in tension. So with a high tensile strength in the badminton racket frame, it helps us to prevent deformation or breakage, ensuring that the frame can endure the stress imposed during intense gameplay. And next is the fatigue strength. The fatigue strength is to sustain dynamic loads and maintain structural integrity. The racket will have to sustain the impact and dynamics loads from the shuttlecock during the game, so it is crucial that the frame structure integrity will remain well enduring repeated cycles of stress. And next is the stiffness. Stiffness is defined as the resistance to elastic deformation when subjected to applied loads. And it can be determined by using the modulus of elasticity E. With a higher E, it means that it has a higher stiffness. And with a stiffer frame, it provides a more efficient power transfer and control over the shuttlecock for the player. And next is the cost. So for the cost, it should be low cost and affordable by the community. So from a research in Bangkok, Thailand, for the people which earns around 20k to 30k baht, they say that they prefer the badminton rackets that has high functionality over the ones which is branded and high cost. And that's all for the key properties. So now I'll be moving on to the comparison of materials. So the materials that we are selected are 6061 aluminium, platinum 6 Al4B, and the last one is the carbon fiber reinforced polyamide. So in this case, I'll be just talking about the 6061 aluminium. It is also known as the aircraft aluminium, and it is one of the most commonly used aluminum alloy in various manufacturing processes, including the making of badminton rackets frames, and it consists of approximately 97.9% of aluminum, 1% of magnesium, 0.6% of silicon, and small amount of copper, chromium, or other elements. And according to my research, it has a density of 2.70 grams per kilometer cube. This low density results in a lighter weight of component, and it is a good property. And the next one is the tensile strength. The ultimate tensile strength of it is 310 megapascal, which means that it can sustain quite a huge amount of stress before failure. The next one is the stiffness. The stiffness also can be determined by the modulus of elasticity E, and in this case, it has a E of 69 gigapascal, which means that it is quite stiff. And the next one is the fatigue strength. The fatigue strength of it is 96.5 megapascal, which means that it cannot sustain too high of a repeated cycles of stress as it is quite low compared to other two. The last one is the cost. The cost of it is $3.1 per kilogram, and this is considered quite cheap, making it more economical choice for manufacturing processes. And now I'll pass the floor to Siak Chun Shi to finish the presentation.
Yeah, thank you, Brian. I'm Chun Shi, and I'm going to continue the presentation. So the titanium alloy that we've chosen is the titanium 6L-4V, or we refer it as the grade 5 titanium. It is one of the most used titanium alloys in the manufacturing, and it is comprised of 90% of titanium, 6% of aluminum, and 4% of vanadium. For its mechanical properties, the titanium alloy has a density of 4.43 grams per cubic centimeter, which is lower than the density of pure titanium, which is 4.5 grams per cubic centimeter. Besides that, the titanium alloy has a modulus of elasticity of 114 gigapascal and has an ultimate tensile strength of 950 megapascal, which means that this titanium alloy is stiffer than pure titanium and can be plastically deformed without sacrificing its structural integrity. The fatigue strength of the titanium alloy is 240 megapascal, which is significantly higher than aluminum 6061. For its corrosive resistance, the grade 5 titanium instantaneously produces a ceramic oxide layer on its surface when it comes into contact with the environment, especially humid environments such as the badminton court. Due to the manufacturing cost and the processing techniques, the titanium alloy will cost about 310 US dollars per kg. And the last material is the carbon fiber reinforced polyamide. The one we're using is the carbon fiber reinforced PA6. So PA6 is often used in aircraft, aerospace, automotive, and other industries. The carbon fibers are made out of polyacrylonitrile, which are good precursor for carbon fibers due to its carbon backbone. The heat treatment between 1000 degrees to 2400 degrees causes oxidation and dehydrogenation, which will produce fibers like high modulus fibers and high tendency fibers. So the density of PA6 is 1.13 grams per cubic centimeter, which is relatively lower than the density of both aluminum alloy and titanium alloy. It has a modulus of elasticity of 2.4 gigapascal, which indicates it has high resistance towards elastic deformation or bending. It also has an ultimate tensile strength of 84 megapascal, which it can plastically deform more before the material fails due to overstressing. PA6 is also known for its good corrosive resistance to most alkalis and salt solution. However, the polymer in the composite is prone to absorb moisture, ranging from 8% to 10%. But by adding carbon fiber through injection molding process, it will help reduce the absorption of the moisture. And its fatigue strength of 459 megapascal for a million cycles testing is one of the reasons it is used in aerospace and aircraft industry. The cost for PS6 is $1.91 per kg, which is relatively cheap considering it requires strict supervision and requirements when manufacturing. And that's the three materials that we've chosen for the assignment. By comparing the three materials, we've decided on the material we want to use is the aluminium 6061. And with that being said, let us discuss about the long-term sustainability and socio-economic considerations. The aluminium can be remelted to be manufactured into new rackets, and in the process, it helps save 95% of energy from production of the raw materials. From the carbon footprint aspect, aluminium is responsible for releasing 270 metric tons of carbon dioxide in 2020 and has an increase of 1.7% in 2021. However, by implying near zero technologies and increase the recycle production, it can help decrease the carbon emission to 220 metric tons by 2030. As for the service life, it has a good corrosion resistance due to the oxide layer, and it has high fatigue strength and ultimate tensile strength, which will aid in increasing the durability of the racket. And lastly, the 6061 aluminum costs $3.10 per kg, meaning that it will cost less to manufacture the frames, which will lead to more affordable rackets for the community. So, as a conclusion, the 6061 aluminum is selected as our material for the badminton racket frame. The reason for this result is because after we've compared the three materials, it is the most cost-effective material amongst the three. Although it has high ultimate tensile strength, stiffness, and fatigue strength, It has a moderately low density and surprisingly low cost to manufacture. It is also recyclable, has a good service life, and it is affordable. Even though 270 metric tons of carbon dioxide is released from manufacturing, it can be reduced using near zero technologies and through increasing the recycled production, making it more sustainable than the other two materials. And these are the references. If you want more information, you can look it up through here. And that's all for the presentation. Thank you for watching, and I'll see you next time.